Alrighty. Good evening, everybody. Thank you so much for being here tonight. My name is Morgan Alanji. I'm an AmeriCorps member serving with Conservation Nebraska's Common Ground program. Conservation Nebraska's mission is to protect our state's natural legacy by educating the public, supporting communities, and increasing civic engagement, which we accomplish through locally led education efforts and community engagement projects to address local conservation concerns. Before I hand it over to our speaker tonight, I do have a few things to go over. As our Zoom audience, your cameras are off and you will be muted throughout the presentation. If you do have any questions, though, we ask that you type those in either the chat or the Q&A section, and we will address those as we go on with our um, presentation. And we will have time to chat about those. Um, Also, towards the end of this tonight, we will launch a survey, very brief, should take you no longer than 1 or 2 minutes to complete. And this survey really does help support our programming, especially doing things like this. We appreciate you taking the time to fill those out and give us your thoughts. So I will be done chatting now. I'm going to hand it over to Nirupam and we will get it started.
Okay, can you hear me?
Yep.
Okay, let's. Can you hear me?
Yes, we can hear you.
Okay, great. Because I'm not seeing my controls anymore. I think Houston has lost its control with the spaceship. But yeah, so I'm Nirupamait. I'm an associate professor of environmental engineering in Nebraska. I was originally born in Bangladesh. If you don't know about Bangladesh, so if you look at United States in this map on the left-hand side, then Bangladesh is here all the way across, like half the world across, and it's a very small country. It's smaller than, um, uh, like even like very small, a little bit bigger than Nebraska, but the population is like really, really high compared to 2 million population in Nebraska. We have about 180 million population. So I I did my bachelor's in chemical engineering back in Bangladesh, University of Engineering Technology. It's kind of considered the MIT in Bangladesh, so it's one of the top schools. And in engineering, then I did my master's in environmental engineering from University of South Carolina. I came to US in 2010 for master's. Then I finished my PhD from University of Texas Austin in 2015, and then I started a faculty position. I was an assistant professor in University at Buffalo in SUNY system. And then finally, I came to Nebraska in 2023. I spent 3.5 years here, and I'm learning a lot about Nebraska, and it's been a really nice experience. So I'll tell what we do. I call my lab. We have a research lab. We do teaching. We do research, and I do research on. We call it Laboratory for Environment, Nanotechnology, and Sustainability. And we do mostly work on water. So we use basically science and engineering concepts to clean water. So the tap water that you drink that are treated by environmental engineering, either environmental engineers themselves or environmental engineering like engineering made treatment technologies, right? So the idea is that we try to find a problem in our water, mostly like our environment, especially in water that we need to clean. And at the same time, these pollutions are becoming harder and harder to clean. There are new chemicals that are coming out that are not easy to clean, like plastics, different types of chemicals, and different types of, and I will talk about that. There are different types of bugs that are there. So it's very difficult to clean. So what we do in our lab, and I do, is we design different types of materials, different types of technologies to take out these pollutants from water. And how we do it is that we design experiments. We do have a lab. I'll show in a bit, and we have do lab experiments. We also are using these new AI tools or computational tools to design new materials or understand if our materials are or technologies are performing well to solve a water pollution problem. So our goal is basically provide design technologies that can provide clean water for everyone. At the same time, if you think about your wastewater, we think like typically municipal wastewater or industrial wastewater, many of them, yes, they are dirty or not looking good, but they also are source of many different resources. So we also try to design technologies that can extract useful resources from wastewater. So the goal is to help the people and the planet by solving the pollution problem from water. So this is my lab group. Obviously not. They are my wife and I are very fond of animals, so we have a lot of dogs and cats of our own, but we also do fostering. So there are some of them. So this is my lab group at this point. There are a lot of students. They can be international, domestic, Nebraska native students are there who are master's, PhD, and undergrad students in the environmental engineering program or in chemical engineering program in the university, and they actually do the lab work themselves and help us design these technologies. So this is our lab, environmental engineering lab in UNL. So we have some spaces for doing the experiments. Then we have really cool instruments, like on the left hand side, bottom right hand side, we have this instrument that this is like $500,000 worth of instrument that we bought, and we have set it up to analyze PFAS. If you are not, which is a contaminant that I will be talking about today. It's a very difficult contaminant to identify first, and if you cannot identify the problem, it's very difficult to solve the problem too. So we are very fortunate that we have got the support of our state and also the university to buy this instrument so that we can help design, identify the contamination. We are also fortunate to collaborate with different other universities over the time, and we are fortunate that federal government has supported many of our projects, like through different agencies, through funding like National Institute of Health, National Science Foundation, US Geological Survey, US EPA. All these different organizations help us in our research. So I'll talk about like the topic of the talk is what's in our water, right? So first of all, the question is, um, have anyone of you watched this movie Dark Waters? If you have not, you can answer in. I cannot see the chat, but if you answer, I don't know how the. I don't remember Morgan. If they want to ask the questions, do they ask right away, or they just put it in the chat?
They can do the chat or the Q&A, and I can
Okay,
let you know if there is anything in the chat.
sure. But thank you for that. I'll just go ahead with this. So if you have not watched the movie Dark Waters, you can you should probably watch it. This is a 2019 film by all these great actors and actresses, but this is not talked about a lot, and many people don't know about it. It's not advertised as much. This is one of the best movies I have ever seen, based on true stories about a chemical class that we use all the time, and which is causing a lot of issues in our health. So this is a movie about how a group of lawyers, scientists, and most importantly, farmers that brought into attention that something in the water was killing their cattle. Okay, so and hurting people in West Virginia. So this movie is about that, and what it talks about is PFAS, or power and polyfluoroalkyl substances, or which is known as forever chemicals. On the right hand side, you see there is a lot of different chemical structures. There are a lot of them. What it means, I will simplify it. This is what it just showing is that there are within this PFAS, fluorinated compounds, there are a lot of them. Like there are about 15,000 different chemicals that can fall into this category. what it does is this is basically this is one like major structure of it. So this is known as PFOA, perfluorooctanoic acid. So what it is basically a chemical made of carbon and fluorine, okay, mostly. So when carbon is mostly a positive uh, element, and then our body is made of carbon. Most of the living beings are made of carbon. Um, and then fluorine is very highly electronegative, meaning they can be very negative. So positive and negative attracts. So when carbon and fluorine are bonded, they create this highly stable bonds. And why this was created is they were created back in 1940s during World War II. So when they were trying to create um, uh, like water resistant coating for tanks, like tanks for war. And that's what they were trying to figure out. And then they found this really good chemical by bonding and carbon and fluorine, because they are very, very highly stable. They are highly resistant to heat, they are highly resistant to water, and they're really highly resistant to oil. So they became very, very important because you could put them in high temperature situation, you could put them in a water repellent situation, you could make a lot of different things based on that. So uh, this is one of the strongest bonds. Carbon and fluorine doesn't exist bonded in nature. So this is totally a synthetic chemical, and this carbon fluorine bonding is very important because they cannot be broken very easily. So they don't degrade. So these are some of the examples of the chemicals that we see, PFOA and PFOS in the two here. These are the ones that are no longer made in US because they are banned from making in US because of their toxicity. So, but there are many other replacement that has come after that. Basically, when companies are told that these are very toxic, you cannot make them, then they start making something different but similar compounds. Okay, so to replace the compounds. So where are these compounds? So if you think about, I talked about heat resistance. If you think about non-sticky cooking pans, that's where you have heard about Teflon or or cooking pans, non-sticky pans. They're really useful for cooking, but the coating on the surface is made of PFAS compounds. So anything and everything, like if you think about our raincoats or rain jackets, our firefighting foams where we can, fire extinguishers have the foams inside them. They also have PFAS. The Starbucks cups or any food packaging that we want to make it non-sticky, right? We think that we are not using plastics by using paper cups in Starbucks or any other places, but we don't know that those paper cups actually have water-resistant PFAS coating on it. That's why we can use them for that type of application. So it's like anything you want, fire repellent, fire resistant, water resistant and water repellent and oil repellent, you would use PFAS in those. So almost everything and anything we use are contain this type of chemicals. Even in semiconductors, so our iPhones, all the electronics that are made in all this semiconductor manufacturing, like the basic part of the iPhones or like electronics is silicon chips. And when they are made in semiconductor industry, we use a lot of fluorinated compounds there too. So this is like a information that came out. And think about, now we talk about all these AI and data centers. Data centers are being built in Lincoln. Data centers are being built across Nebraska, across the country in many places. So so those data centers are made using these hardwares, but also these data centers also have need a lot of different other stuff like cooling mechanism. Like these servers in data centers can become very really really hot, so you have to cool it with something. You can use water, but water, you need a lot of water to cool them. So they are making new type of coolants that actually use fluorinated compounds. If you think about refrigerants in our AC and refrigeration or freezers, they are made of some type of fluorinated compound too. So they're everywhere. So PFAS is everywhere. What that means that we can get exposed to those PFAS chemicals from different types of products. We can ingest them, we can inhale them, we can uptake them through skin exposure too. So they are everywhere, and that can get inside our body. We can also drink them through our water systems, like our water is contaminated with PFAS, and that's what I'm going to talk about. What happens after exposure? After exposure, there can be many different diseases that can happen. So basically, it is found that these are carcinogenic compounds. They can also create these different types of disorders in kidney and decreased immunity, then also developmental disorder in babies. There are a lot of diseases that are directly caused by PFAS exposure and this. So this is another example of how we can get exposed to PFAS. Like we can even like food. These are a couple of examples like food and food packaging. Like PFAS are used for grease-proof liners and packaging, like takeout containers and pizza boxes. So from there, we can get PFAS exposure. We can have drinking PFAS in drinking water, and we will talk about that later. There are a lot of dust, like even the carpets that we used in home. Carpets are made. A major ingredient in carpets is PFAS, because you don't want your carpet to have a lot of water, like water soaking to happen. So waterproofing is needed. So we have all these things and we can get exposed to them. This is again the same slide about that. So how does PFAS, how do we get exposed in through water systems? So because we are talking about water, so we use PFAS in different aspects. So from your municipal usage, mostly in urban areas, you can have PFAS coming out of that there and go to our municipal wastewater treatment systems. Okay. And it can be coming from industries too, like all these industries that are manufacturing PFAS or using PFAS. They can also, the effluent of these or the wastewater from these industries that can come to, that can contain PFAS can come to wastewater treatment plant. Once they're, the problem with our wastewater treatment plant is that the conventional wastewater treatment plants were not designed to take out PFAS. And one of the issues with why we didn't know about PFAS yeah, for many years, because they were discovered in 1940s, because we didn't have the analytical capability or instruments to identify PFAS in water. The reason is that PFAS can be released in very, very small amounts, that it's almost undetectable, okay, by regular techniques. But they still exist in diluted form there. So when and at the same time, our wastewater treatment plant is not capable of taking out PFAS from water. So what can happen? One thing can happen, that if they are not treated well, then they will go and when we take out the wastewater effluent to merge, like treated effluent to merge with surface water or groundwater, that they can reach there. The other thing that happens, there is a process called biological wastewater treatment process, where there is a lot of bacteria is used to take up nutrients from water, like nitrogen, phosphorus, that type of thing there. And then these bacteria die and create this whole solid, a lot of solid, which we call biosolids. Now, these biosolids, we create a lot of them, and these biosolids contain a lot of different types of nutrients. So a lot of these biosolids are actually used in different farmlands. In Nebraska, 95% of these biosolids are used in actually farmlands. So the issue is that if PFAS is getting in the biosolids, then when we are using them in farmlands or anywhere we want to put for land use, then there is a possibility that PFAS can leach out from there and go to groundwater, go to our food, go to the kettle, like all these things can happen. So that's exposure to the environment. The other way, once we want to get the drinking water, right? Either this is in drinking water or in private wells, like in urban systems or in rural systems. So because our surface water and groundwater are polluted with PFAS in many cases, although it's in very small amount in many cases, um, but they are still polluted. So our drinking water treatment plants, the conventional ones, meaning the regular ones that we have now, they don't really have a way to take these PFAS out. So we are still, in many cases, we're still drinking PFAS contaminated water. I don't think like Lincoln or Omaha has issues with drinking water PFAS issue, but many other places can have, and especially in rural areas where things are not regularly monitored and everything, um, it can happen. There are cases like that. So the issue is that PFAS is not only going into municipal or residential home to wastewater, then they are coming into the soil, then from soil they can go into our food, different type of food, vegetables, milk, or even in beef or pork. So there are studies that show that there has been a lot of uptakes of PFAS in these places. Like in the state of Maine, they have already banned any biosolids application in farmlands because of risks of. There has been a lot of cases where they have lost businesses and they have lost like cattle because of the PFAS contamination, because in those areas there are large PFAS manufacturing industries, so from where they got some contaminations really bad, um, and that led to those situations. So many states are thinking, Minnesota is thinking about that too. But like for example, this is a case from Texas. So this is an article that came out in 2024 in New York Times. They did a series about these forever chemicals. I forgot to mention like why they are called forever chemicals. The reason they are called forever chemicals, because I talked about these carbon fluorine bonds. The carbon fluorine bonds are so strong, it's not, it cannot be broken by natural systems. So that's why they can live, these chemicals can live in water or environment for a long, long time. Like their half-life is in 100 to 1,000 years half-life, which is a very, very long time for any chemical. So chemicals, we can have chemicals, synthetic chemicals, as long as they are degrading in nature by microbes or other processes within a short time, then it's not a problem. But when they stay in the environment, they become a problem because our body or plants or other organisms or other animals are not equipped. Our body is not equipped in dealing with uh, non-natural chemicals in many cases. So having forever chemicals create a problem like that. So what happened in Texas is basically there was a cattle from a ranch from where a calf was stillborn. Basically, it was born. It was dead before it was born, and they took the carcass of this calf to Texas A&M University. They found its liver was full of 600,000 per like a PFAS, 600,000 parts per trillion. Okay, now I'll give the context. I'll have to skip this slide. So what I'm showing now, US EPA came out with a limit back in 2024 uh, of these chemicals. Like if you look at this contamination level, so this is like how much chemical, PFAS chemical can be in our drinking water. What is the limit? So if you look at this top two, I'm not going into the other ones, PFOA and PFOS, their maximum contaminant level that is allowed by EPA to be in our drinking water is 4 parts per trillion. The PPT means 4 parts per trillion. So if we go back here again, this is 600,000 parts per trillion. So you can imagine like it's like it's a humongous amount of PFAS that was in the liver of this calf. So that got into the calf or cattle somehow from some sources. So it's also important that we should be thinking about how PFAS is going into our agricultural land and ranches, and if our animals are getting impacted. So I'll just give you an example what we are trying to do now in UNL. We have a project. I have a colleague who does looks at biological processes. I look at physical processes, chemical processes. So what we are looking at, if PFAS is PFAS containing biosolids or biosolids in general, wastewater biosolids in general, is applied to a farmland, and if there is a rainfall, then we will have agricultural runoff. And this agricultural runoff goes into the river, lakes, and other places. So we are collecting water samples from Elkhorn River. Is there any question, Morgan?
Yes, we do have a question. Um,
Sure, go ahead.
one of our, yes, they're asking, is there a way to test levels of PFAS in our private well?
E, e, yes, like we we have we have to sample them and we have to test them. There are ways to test it. It's a sampling process. So I was going to come into this point that PFAS analysis is more of a costly, expensive thing. That's the To give you an example. So we many of us know about nitrate issues in Nebraska. And to test nitrate, you can use a test strip to just screen for nitrate. You can just take a paper strip that costs less than $10 or probably $10. You can do that to understand, oh, if there is nitrate at above a certain level. You may not get the exact accurate value, but you can actually get some understanding. The issue with PFAS is the instrument that I showed in the beginning, one of the really cool instrument that we have in the lab. So for PFAS analysis, that instrument needs to be used, and it takes much more cost. That's the issue. All the samples can be done. So to give the context, so $10 for nitrate. Typically, if you go to commercial labs for PFAS testing, it will cost $500 to $700 per sample. So typically, when we are sampling any contaminant, then we try to test at least 3 times. So if you are looking at 3 times 500 to 700, it's going to cost $1,500 to $2,000 per to get a really good uh, uh, assessment. So that's where the issue is. But to the point that if they can be analyzed, yes, we can analyze them. We have at UNL, we have two different facilities. UNL Water Science Lab, they do water testing. They for like any type of sample. We do our environmental engineering lab. We have the instrument that I showed. We have developed methods for testing water samples. We can also do that. Uh, we still didn't do it as a service. I'll be honest, like for others, we are just using that for research purposes. But we can obviously test for a price. We didn't decide what will be the price yet, but Water Science Lab, I think they're much cheaper compared to the private commercial labs. I think they go about $300 to $500. But if you go to the Water Science Lab, but it will be in that range. So wherever you are getting that samples done, um, like per sample cost. And yeah, I gave a more detailed answer, but just to give you um, a context about what would be the cost and everything. Anything else, Morgan?
Yeah, yes, we have another question. They're asking, will a reverse osmosis system remove PFAS?
Yes, in most cases they would. Um, the issue would be to test Reverse osmosis is a great choice. It adds energy cost, but for home usage, it's a really good thing to use for taking out PFAS. Most cases, it's very efficient to take out PFAS. But still, like there can be a situation that, oh, it's keeping that. So, but in most cases, reverse osmosis is very good. Anything
Wonderful.
else?
That's it for the moment.
Okay, sounds good. So, um, coming back to the quality cost cost aspect. So the other issue is that when we are talking about individual homes is one thing, but when we are thinking about a community, so for everyone to buy reverse osmosis, replacing it continuously, because reverse osmosis can do that, or activated carbon also, like our Brita filters, they can also take out a lot of PFAS in many cases. But the issue is how fast the reverse osmosis or the activated carbon you need to replace. That becomes an issue for a person. So on the other side, if we try to do in an urban setting like treatment, then we are thinking about water quality utilities like across the country in US to invest almost like 200 billion to $1 trillion capital cost, so that we can take our water like water like PFAS concentrations to the levels that EPA is regulating, like 4 parts per trillion. So there is a cost to that, right? So it's actually solving the problem is a really good thing. It's needed for us, but we are getting the cost burden. The public is going to pay for it, and not the companies who are making these chemicals, polluting this environment, like creating these chemicals for us. So they're very useful. These chemicals are very useful, but it is also adding a lot of problems for us. So PFAS regulations in US, what I said, like these are the two chemicals that are mostly regulated on the state level. Many states have their own drinking water limit. Nebraska doesn't have one. They just follow the federal regulation, but but like Minnesota, New York, Maine, State of Mind, they have their own, and they started even before the federal regulation came. Many of the states started their own regulations before federal government. So, if you want to know how much PFAS is in water, in many cases, so this is called Environmental Working Group (EWG). You can search with EWG. It doesn't have every single data point, but there is a lot of data point out there. EWG working group. It's an interactive map. So basically, you can go to this uh, map, and I will show. I can, if I can show you. But if you go to this map, you can actually zoom in to Nebraska, and even if I zoom in, I don't know if I can zoom in. It doesn't do that for me. But if you zoom in, then you can identify. So if you look at this left-hand side, drinking water, then military sites. Military site is important because most of the PFAS, high concentration PFAS contamination, is in military sites. It can be Army, Navy, Air Force. For example, Offutt Air Force Base has a huge PFAS contamination, and that is because all these military sites, Army, Navy, Air Force sites, they train a lot with explosives. They are using a lot of ammunition. When they have these explosions, they have to use firefighting foam to take those fires out. So at that point, what happens then? You are dealing with all this PFAS that has over the years they have done it. So a lot of PFAS got into the environment. They are contaminating the soil and water in those places. So highest concentrations of PFAS are found in around military sites and in military sites compared to anywhere else. And you can go to this link. EWG. You can just search with EWG PFAS interactive network, PFAS interactive map. I don't know why my laptop is not working well. Okay, let me get back to, okay, this is not working. Okay, so here is the thing. You asked about reverse osmosis. Will reverse osmosis work? So this is PFAS treatment, kind of like which technologies work, which technologies are not working well. So if you look at this on this one, like on this right hand corner, upper corner, so you see reverse osmosis is very high efficiency, but it also has considerable cost. Okay, and the full like circle compared to this half circle, like with a void inside, means this is not fully developed technology. This is fully developed technology: nanofiltration, ion exchange reagents. These are the three technologies that can take out PFAS most of the cases. So reverse osmosis can actually take out most of the thing. Now, why high cost is that it can it 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 is actually, you have to replace, or you have to keep replacing the filter over and over. It requires high pressure. Reverse osmosis means it has very, very small pore size filter. So you are pushing the water through it at very high pressure. So that adds a lot of energy cost compared to, and when we are trying to do it at scale for a large community or for a city or for a large water treatment plants, reverse osmosis is probably not the best thing to try. Okay, so and there are a lot of technologies. Most of these technologies actually just take out PFAS from water. But the other issue that we have to think about, just taking it out from water is not going to solve the problem. So what the reverse osmosis does, it is a filter. So it's one side, the water is coming through one side, the other side is capturing those PFAS. Now, this is becoming a very small volume, high concentration PFAS, uh, like liquid, right? PFAS containing water. So what do you do with that? You have to throw it out somewhere. At the end, all these are piling up somewhere else, or you can send it to landfill. But over time, they may also leach. So the other part of the question is PFAS treatment. When we say treatment, can we destroy the PFAS chemicals? So that's where the thermal process comes, electrochemical process come. Can you burn them out, burn them off? A biological process can come. But the biological process, as you can see, low efficiency, low cost. So bacteria cannot degrade these chemicals. They cannot break the carbon fluorine bonds. So there are different ways we are trying to do that. So this is where my research comes in. We do a lot of research on like just understanding conventional technologies, but also we try to develop new materials, advanced materials for taking out PFAS from water. So this is some of the conventional technologies that are effective. One is granular activated carbon, anion exchange resin, and also membrane separation RO are very generally effective for removal. They are more effective for long chain PFAS like PFOA and PFOS compared to short chain PFAS, like where carbon numbers are small. And then removal efficiency and cost depend on source water characteristics and water systems characteristics. So if you are treating groundwater, that might be easier compared to treating a surface water. That's what it means. So this is like large scale. Like you were talking like typically we talk about home reverse osmosis system, but this is like large scale reverse osmosis and systems for large scale treatment. So you can have these different types of water treatment systems. Yeah. But again, what I said, the issue, it doesn't end there. So we have a lot of residuals, like we separated the chemical, but also we have to treat them, right? We have to destroy them. So how do we do them? Either we put them in landfill, or can we reactivate or destroy in a different way? Or, but the other issue is that can they go into our environment? So this becomes a problem. So that's where, so as you can see here, it says there are no known commercial treatments for RO concentrate streams or regenerate solution. What it means, when we are using reverse osmosis, at one point we have to change it out, right? We get a new filter cartridge. So by that time, the one that is thrown out, it contains a lot of PFAS in there because it cleaned your water, it has those PFAS in them. What do you do with it? There is no commercial solution yet that can destroy the PFAS to like in the reverse osmosis filter that we are capturing PFAS. Okay. So what we do, we use nanotechnology or nanomaterials in our lab. I'll give a brief introduction of what we do. Um, and if you don't know about nanotechnology or nanomaterials um, so what I will say again, we go back to the electronics. So we have come from this first generation of computers, which were like huge size, one computer in a room, huge room. We have seen these wireless phones that were like really big. Now we have smartphones. We can do so many different things with smartphones and digital technology. How do we came about that from large scale to small scale? I'm not talking about PFAS anymore. I'm talking about the solution part here. So what we do is we take very large scale materials, we make very small scale materials now. So we came from like really large electronics to very small smartphones. How we do that? We came from chip. When we talk about chip, semiconductor chip, the basic part of it is transistor. So the large scale transistor that was created in 1947, this is one single transistor that is the basic part of any electronics. And if we think about iPhone 16 itself has 16 billion transistors inside it. So you can imagine that this transistor went so small that we can create those technologies now. So nanotechnology is basically, nano means it's 10 to the power minus 9 meter. It's very small atomic scale material. So we are taking small particles and making the work happen that we couldn't do previous like previously. Okay, so these are like this type of materials, like these are solid particles, like think about like any sand particle or something. So when we take these different sizes, shapes, um, structures, chemistry of particles, they can the idea is that these particles, based on their properties, can do a lot of things that are not possible in bulk cell. So what we are trying to do, for example, if you think about gold in larger scale, gold is yellow in color, right, or golden in color, right? But when we go into the nanoscale, if you look at this, we can create nanorods, we can create nanoshells, and they can have different colors based on their aspect ratio, meaning how much is the length of the nanorod versus the width. So they can have different colors. What it means that instead of having just a single color based on what the structure is, what the length is in nanoscale of these nanorods, nano gold, you can have different colors. That means they interact very differently with light. That means they can have different properties. And that properties help us to design different electronics, different types of like cancer therapeutics, different types of vaccines, all these things, drugs. Also, we can, drugs means medicine. We can create those using nanoparticles. And we have done that for many years. So what we do, we design actually new type of materials, nanomaterials, and we use them. This is a long thing. I'm just going to say that we design this type of nanomaterials, use this type of nanomaterials to take out PFAS from water. So one of the things we do, this is a carbon-based material, like you know about graphite, that is pencil lead. So this is, if we could take out one single atomic layer of graphite, so that would look like this carbon sheet. And then on top of this, we put iron nanoparticles. So carbon and iron. So this becomes something which can capture PFAS. So this is called adsorption. PFAS can be captured on the surface. And then we do some reactions. We can do also some reactions to degrade the chemicals from the surface. So this is one way of So my first PhD student, Dr. Arvid Masood, he designed this material to take out PFAS from water. So this is the way we do it. We take PFAS solution and mix it with the nanomaterials. We try to see if the nanomaterial is taking out the PFAS from water by doing this analysis in the process. Um, and then we try to figure out if the PFAS molecule is breaking down. So if you look at this one, the bottom figure, this is what it shows, that slowly with the reactions, some of the PFAS atoms, so like fluoride, some of the fluoride is going out, some of the carbon atoms are going out, oxygen atoms are going out. So we are degrading the PFAS. It's not only separation, but also degradation or destruction of the PFAS molecules. We are also trying to create 3D printed filters so that you can put them in the tap, like water tap there. You could add that at the faucet. Can we design type of a new nanomaterials based filtration technique that could take out PFAS from water and destroy them too? Okay. So then the other question that you asked, like, PFAS analysis, can we do PFAS analysis? One of the challenges I said, like PFAS analysis is expensive, right? And now we are trying to use nanosensors. It's not us. I have a collaborator in New York in the Clarkson University. So they are making different type of sensors which could detect PFAS in water at a very fast rate within minutes or within a few minutes. Can we make that happen? And it would be very cheap compared to what we can do now. So this is a project funded by US EPA. We are trying to do that, develop that sensor, but also we, like from my group, we are trying to see if we can design materials that could destroy the PFAS. So it's like, can you detect and destroy PFAS at the same time? So we are trying to do that in this project too. So I believe that's it. So I just wanted to give an overview of what the PFAS issues are, why we should care about them, and then what our group does. With that, I will take more questions. Like we have some 10 minutes, 12 minutes. Yeah.
Um, yes, if anybody has any questions, please feel free to type those in. And if everyone doesn't mind, we'll go ahead and launch that poll while we're wrapping up here at the end. I do have a question. So
Sure.
I know earlier when you had mentioned, you can find the PFAS, I think you mentioned like in Starbucks, like to-go coffee cups or parts of firefighter suits or, other things some things that are like daily household items. Do you foresee or like get general feedback that this is something that can eventually be eliminated? Or I mean, it's called the forever chemical for a reason, but is there an outlook that says we can really get a handle on this, or is it something that, is just it will be researched, but it will, like I said, forever be around?
That's a very good question. So many of the companies, including Starbucks, actually said that they're not going to use PFAS anymore. Okay. The issue is there are multiple issues. One of the issues is that when they define what PFAS is, may be very different than what we define as a researcher and as a concerned like scientist, or by the definition that Europe comes. What is PFAS? So many times companies are trying to evade what PFAS is. Their whole point is, oh, you said initially, oh, PFOA and PFOS are the PFAS. Now you are saying, oh, all of these are PFAS. We don't take that. As long as federal government is not saying these are the PFAS that we should be caring about, we are going to use a different kind of PFAS, but we are not going to tell that we are using a PFAS. Uh, we are just gonna call it by its name, so you can't really uh, like say anything against it. So it's a play of words. But many companies are now taking action. Like think about um, not only Starbucks. Starbucks said, then a lot of food packaging, other companies, then even what is that? North. There is this jacket company, really popular. Uh, North. I forgot the last part of it. Uh, like all these like big
Like
clothing
North
companies.
Face or Columbia.
Yeah, North Face and Columbia, and they also pledged that they are not going to use PFAS. But now, and we have also talked with semiconductor companies. The issue is that what PFAS provides as a property, behavior, chemistry, it's very difficult to do the same thing with other things. So it's a very challenging thing. What I think is that it's going to be very difficult to eliminate all the different PFAS from being used or manufactured. It's going to be that. So we have to figure out which PFAS are more safer, which PFAS can be used a little bit safer, or which PFAS can be still be used if we have a management plan on the waste side, like when they are going in the wastewater or when they are in the environment. So if we have a plan for that, and if we can figure it out, that would be, because replacing the issue, for example, when we talked with semiconductor company Intel, and their point was, look, developing a technology, just one instrument for our 100 different instruments. If we change a PFAS chemistry and we try to replace it with a different chemical, then it's going to take 10 to 15 years for us to develop that technology itself, develop that machine to create new computers itself. So it's almost impossible to do it. So it depends on which products we are using. So for semiconductor, if we have a wastewater treatment plant that can handle PFAS, that's one thing. For food or direct interaction, where humans or other organisms have direct interaction with PFAS containing products, I think banning them is more important. I'll give you another example. Like if you look at different states, many different, like Colorado, Minnesota, New Jersey, they are banning a lot of different products that contain PFAS, even dental floss. Like the dental floss itself is a piece of Teflon itself. That's why this is so useful. It works as a really great floss, but it has PFAS in it. So I think it depends on how we should identify and which products we should ban, and how we should say that, oh, this cannot be made with PFAS. Not everything. Uh, we cannot do it. It's another big problem too. Yeah. Sorry, Morgan. This is like really long answer to your question.
That's okay. That's okay. Um, we do have some more questions. One of our audience members is asking, do we absorb PFAS through our skin?
Yes, we do. Yeah. I don't have the actual quantification, but one of the three major ways how we get PFAS in our body is skin, like dermal exposure. So yeah, we do that.
Yeah. Another question is they're asking, would a water softener system affect PFAS levels in household water?
Like PFAS softener system itself shouldn't release PFAS, but if um, it's a good question, it will impact. It can be a good thing or bad thing. Like I have to do a little bit research to get back to you. I'm sure somebody has tested that, but I don't remember on top of my head. But it will impact a bit. It may. I think it will impact. I don't know exactly which direction.
Okay.
Yeah.
Um, Perfect. I would also meant to ask if there was more questions that anyone had for you, if they would just reach out to you through the your email there at
Yeah, email.
UNL.
Yeah, that should be fine. Yeah.
Okay, wonderful. And I will also need to mention that this will be uploaded to our YouTube channel, but I will also follow up with everyone and I can include that information there if there's more questions after. Um, and then
Yeah.
somebody else is saying, so it just says chewing gum has plastic components too.
Yeah.
Not, yeah, not
Yes.
necessarily. Yeah.
Yes. So actually, one of my friend actually did from UCLA, Dr. Sanjay Mohanty. So their group did a study, and it was all over the news a few months ago, like BBC, CNN, everywhere. And they really the main thing they tested is what type of plastics are getting out from our chewing gum, and when we are chewing the chewing gum. Yeah, that doesn't mean it will be harmful. Okay, it's not necessary that that is the case, but it's concerning. We should be careful about it. But that doesn't necessarily mean. So there is a little bit difference between chemical versus particles. So whatever I know, I understand so far, I'm not saying that it's not concerning. Our body is like human body and like is really good at filtering particles than chemicals, because what happens with PFAS, it's mainly made off of carbon, and carbon, like the way it works, it doesn't want to stay in water. So when we drink water, it wants to get to our cell. So they attach to the cell and change the composition of the cell, and it can cause cancer that way. For particles, it's much harder for particles to get absorbed like that. It's not like they don't get absorbed, but most of the particles we ingest, and we actually do drink even microplastics. Like if you look at literature, there are some literature how much plastics come out of water bottles when we drink water. So but our body is really good at taking particles out more than chemicals out. Okay, so it tries both, but I think PFAS and other like similar type of chemicals have a different way of functioning that makes it more of a problem. Plastics don't do that much of damage yet, but there is a lot of research going on in that area, and there is a lot of people working on that area. And I'll tell you, at UNL, Dr. Yusong Lee and Dr. Shannon Bartelt, my colleagues, they are working on that aspect, like how it plastics go from applications to environment, or like Dr. Isongi, she's doing research on how like plastic content, food containers. It can be plastic bottles, water bottles. It can be food, baby food packaging, baby food like that come in plastic. When you microwave them, how do they release like small plastic particles, and what happens with them? Yeah, it's a huge area of research, and there are concerns.
Yeah. We do have another question. They're asking if PFAS used in farm weed fabric released into soil at a constant rate, or is the breakdown faster at installation or after a few years of exposure?
That's a great research question. I need to. This is the first time I heard about it, that it's in farmweed place.
Yeah.
So, if anyone has any interested in like doing that research, we would be happy to collaborate and figure it out. It will depend to answer the question. So that one part is there. We don't know. I don't think it will be in the installation. So PFAS is released over time. So all the consumer products that we use, PFAS, as I said, like PFAS is really difficult to degrade. So when they are released, it's not. So if you start cooking now, that doesn't mean PFAS will be in your food all the time. That's not how it works, uh, because they are already heat resistant. So it's not going to be released right away. It can be released, say, over time, when there is a wear, tear here, there. Um, from that process, PFAS can be released. Yeah, I don't think it's gonna happen during installation.
Perfect. That does conclude our questions. We do just have a comment. Somebody wanted you to know that this was very interesting, and thank you for your time.
Okay. Thank you for
So,
inviting. Yeah.
yes. So
Thank
yes, that will conclude tonight's event. Like I said, I will send out your email with those who attended. This will be able to be viewed on our Conservation Nebraska YouTube page in a few weeks. So if you have questions or anything else, feel free to forward those over to Neurapalm. And thank you, everyone. Have a wonderful rest of your evening.
Yeah. Thank you everyone for joining. Take care. Bye.